So, folks, we are recording. And I'm letting you know so that you are aware that you are being recorded. All right. And this is where we were left last time. Is element is easy to understand, right? Again, we say, okay, is the given character a part of this part of the set? Of course, you now know that, for example, if the element is, let's say, like the character is just the open curly brace or closed curly brace, then you can see that actually this is going to return true. So is this what you want? I don't know. But my point here is that not necessarily the semantics of this one. This might be what you want or might be what you want. So you can fix it. But this is the simple part of the problem. So this is size 1 problem. I look at your current string. This is your current string. I look at your first string, first character. I do what I am trying to do with this one. I'm asking, is this your element? If that is so, then you are done. You are finished. Go. If that is not the case, then what we do, we go and look at the rest of the thing. But the rest of the thing is, if this is a size n problem, this original problem, the rest of the thing is going to be size n-1 problem. So this is a perfect case for a recursion. All right. So let's look at another one. Is a set, for example, is the given character string a set? How did we say that? If it is empty, it could be an empty set. This is fine. If the element is element, so one of the things that we want to do, a set, by definition, should not have repeating entries in it. This is the thing that is gonna check, not the, let's say, the format of the specific string. It's gonna say, okay, if you have, for example, A, B, this cannot be a set because a set cannot have repeating entries in it. So it's gonna look for the first entry and say, okay, is this an element of the rest of the set? This is how you check it, right? So you say, is the first entry a part of the rest of the set? This is how you would do it, is element. If this is the case, then you cannot be a set. This entry cannot be, this string cannot be a set. Otherwise, I will check for the rest of it. But if first one, so I'm this one, I'm taking my size 1 problem is this. I take this character here and I say, okay, do you repeat here? If yes, then you are not a set. If no, then I will go and look at the rest of the thing again as a recursive call. So this is size n problem and this is size n-, right? A subset problem. Let's look at the subset case. I am giving you 2 strings and I'm asking if the first string is a subset of the second string. This is what we want to do. So how do we actually get this one? We have in the subset thing, what we need to do is we have one string here. We need to do is, assuming that they are sets, meaning they are not repeating entries, then I will actually check this first entry and then see if this first entry is somehow in this set. So is element, if this is the case, then size 1 problem is take the first entry of your, which is the first string, check if it is in the second string, meaning if it is an element of the second string. If so, then you might be a subset of the second string, but you need to check the rest of it. So you go and check the second character, the third character, and so forth. Otherwise, if that is not the case, then you are done. You cannot be actually a subset of the second character, second string. But if the first string is empty, I know that an empty string is a subset of any given set, or empty set is a subset of any given set. So what I do is I do this one. I look at the first string, first set. If it is a subset, it's an empty set, then I know that it should be subset of the second one. What is? If not that, if that is not the case, then I look at the second one. If my first entry of the first string is an element of the yes, if no, then I know that this cannot be a subset because there is an entry in the first set which is not part of the second. That is the definition of not being a subset, okay? And then otherwise, I will check the rest of the string in the second. If this part is agreeing with, then rest of it should be a subset as well. And then the rest, and the rest, and then the rest. So this is a very, very good and simple recursion. My original problem is to check if the first character of the string is is included in the second one. If not, then I'm already done. I don't need to do anything further because I know that that is not correct anymore. If the first one is part of the second string, then I will check the second part, third and fourth and fifth and so forth till the end. And at the end, I know that if the first string is empty, then it must be the part a subset of the second string. And empty string is always an empty set is always a given set, whatever the set is. This is always all right. So what else did we have? We had reduced unions. So what do you mean by union? What do we mean by union? Union is something like this. If I have A, B, C in the first and a C, D, E for the second one, the union of this thing is going to be A, B, C, D, E. Of course, it doesn't need to be sorted this way. Perhaps it could be something like this, right? A, C, B, B, A, right? So the union of this is going to be A, C, B, X. So how do I do this one? This is very simple. I check if the first set is the first, there are two sets, set one and set two. If the first set is an empty set, then the result is second set. And I just make a copy of the second set into a thing, and I return that. This is the function is actually this way. I take two const strings, and I return the answer, the union, in another one, a third string. Okay, this is how I do it. I take this. If the first string is empty, the answer must be the second string. Okay. Otherwise, this is what I do. I check if the first entry is included in the second string. If that is the case, then I forget it. I don't do anything because it is all in the second one, and I have to go to the rest of it. This is my recursion now. Check the first string, first character in the first string. If it is a part of the second string, forget about it and go for the rest. Go combine union this guy with this guy. So after this one, try to union CB and BAX. Because CB union BAX is the same as CB union BAX because A is repeating here, so I don't need to worry about A. Then CBUX, what I need to do is in this case, if this is, for example, this one is not in the second one, then I have to actually do something about this one, and I would actually put that into my result here. So if this is the case, I just do, if the first character is in the second string, then I just actually do a call to set union with the same argument for the second set, but the first set is actually the rest of the set, not the first character, first entry. All right. And then what I have here is that if that is not the case, what I'll do is the result is going to be this guy times the rest of the union. So this guy is set1, 0, and the rest of it is actually this guy. I need a temp variable here. I need to keep this in the temp variable as we did before with the capital letter, if you recall. And I will actually have this the temp variable kept in here. So the result is going to be kept. The rest of the result is going to be kept in a temporary. And I'm going to actually put the temporary result along with my first character of the first string and put it in my current result. And I will just output it. This is very simple, all right? And then the printing is very simple. Just print it. And you can print the first character. And then the rest is actually this way, right? Printing like what we did before, counting and something like that, is the print the first character and then print the second character. Print the rest of the thing. So if you have a string like this, you print this one. If the string doesn't have, let's say, if the string has only one entry, just print it and done. If the string has more than one entry, print the first one and then call the same function with the rest of the string. So here I'm calling the same function with the rest of the string. This ampersand str1 means that I'm actually not looking at the first character, but second character and on will be an argument to the next function or the print with commas function. Print set can be actually done that way and so forth. I don't know. And get set is actually reading a set from the user. It's not a big deal either. You can see that this is actually all these operations, these set operations, by definition, they are actually quite recursive in math anyway. So it's not surprising that we could do all of it without any loops, but all with recursions. All right. Checking the if an entry belongs to a set, looking at a subset relationship, you're looking at a union, constructing a union of two sets, and printing a set and so forth. These are all very simple recursions and very easy to code. When the recursion is simple, the coding will be simple as well. Okay, so let's look at another problem. This is going to be a fun problem. This is a game. And this is a simple, I think, let's say a puzzle. The puzzle is this. You have 3 pegs. You have one peg. Peg is one of these, is a peg called peg, right? So there are 6, let's say. And you have disks that is actually that you can actually put onto these pegs. And here I show you an example where there are 5 disks, and each of these disks are actually different size. Size gets from larger to smaller. Okay, so the problem is a simple one. So given this configuration, you want to actually put all those things on the start peg to put it on the end peg using we call this additional or auxiliary peg, using that or whatever. So you can use any type of action you want, but you want to go from here, this configuration to this configuration. But there is a important thing that you cannot have. Hold on a minute. Okay, where is my? Hope I didn't forget about those. Okay, let me see. Oops, daisy. Okay. Apparently I didn't save that. That's a mistake. One thing that you cannot do is you cannot have a configuration like this. For example, a smaller peg here. So you cannot have a configuration like this, a smaller peg. On top of it, there is a larger peg. This is not allowed during the your operations. Whatever you do to get from here to here, you cannot have something like this happening. This is not allowed. All right. Meaning you can think of that actually the larger piece is heavier and it can crush the smaller piece. And the larger piece should not be on top of the smaller piece. Okay. So this is the problem that we want to solve. And the original problem is you may have a number of these disks here. You can have many of them. In this case, I have 5, but you can have 6, 7, 8, 9, whatever. And the thing is that can you actually write an algorithm or a C program that can do this one? So you can think of, let's say, the way that you can actually do this one is let's look at how we can represent this problem first, right? So any ideas how to represent this problem in C? How can we actually represent this problem in C? Any ideas? So how many people are here? So there are 66 people, probably because of the sound quality, some have left. All right, that's fine. Okay, on the 66, this is not very good, but anyway. Okay, so soruyu anlamadık diyor arkadaşım. Okay, I'm asking you again. The question is this. I want to solve this problem. I want to write a function like, let's say, solve a tower of Hanoi. Okay, and I want actually, first of all, to write a function like this. I need to represent this problem. So you say, okay, give me n number here, just n. N meaning I have that many disks to start with in the first one. And I want to actually put them all so that this algorithm is going to actually put them all into this one without doing something like this. All right. So how do we represent this in C? So how do we represent, let's say, this condition, this one? Okay, someone is saying, okay, we can do, so this is a tower. So he's saying the start tower, auxiliary tower, and end tower, we can represent them as arrays. All right, so why not? So we can say, perhaps, let's see. So this is how we can represent it. We say, let's say integer, okay, start tower, right? How many entries should be? Whatever the maximum number. So I define here a maximum number, max height of Hanoi. Let's say that this is 20. You cannot have more than 20. This is the largest tower that you can have. And then start tower is gonna be max h. All right, so this is one possibility. Auxiliary tower is again also max h. And end tower is also max h. Okay, so these are the variables to keep them. So how do we actually represent this one? The first condition. What is the first one? The starting one. What would be in these arrays? Start tower array, end tower array, and auxiliary tower array. So each of these arrays had, I don't know, so many entries. So how do we do that? Let's see if there are any answers. Okay, so how can we actually fill the arrays to, let's say, capture this? All right. So if you are talking about an n number or n, right? So you know that. So let's say that one possibility could be something like this, right? So I say, okay, my array is actually ordered this way. The first entry is the bottom one. Bottom has 5, then 4, then 3, then 2, then 1. Right? So this is, if I have 5 entries, this is this one. The other one is, I don't know, is empty. Perhaps empty is -1. 80 is also empty, -1. Perhaps. All right, this could be one way. Okay. All right, let's see. What if I have some configuration like this? For example, let's say that I put this guy over here. So 1 is here now. What will be the change in the arrays? So what is the arrays? Someone tell me. Okay, let's see. So start array is gonna be, so it has still 5, it has 4, it has 3, it has 2, it doesn't have 1 anymore. It has -1, it is empty there. And then auxiliary tower is actually having just 1 and the rest is -1 like this. And end tower is all -1s, right? So this could be one way of actually keeping things. I don't know, right? So if I actually now put, let's say 2 here, this is 2, what will be the array representations for 2? Start array is gonna be what? 5, 4, 3, -1, -1. End array is gonna be 2, -1, -1, -1, -1. And auxiliary tower is gonna be 1, -1, -1, -1, and -1. Okay, so this is the representation that I can use. All right. So I'm trying to see how we can, let's say, do this one, right? All right, good. So let's discuss. So this is a way to represent these tower configurations in C. This is one way of doing it. All right, there might be other ways, but for the time being, this is fine. So let's look at how we can solve such a problem. The solution to this problem is something like this. Think about it this way. If I give you just a problem with n equals 1, what is n equals 1? What is the problem with n equals 1? N equals 1 problem is actually simply this. Let's look at this guy here. Discard this. Let's take this guy. N equals 1 means this is my problem now. Not this guy, but just this guy. So n equals 1. How do I solve this one? If n is 1, and if you have, let's say, this thing, how do you solve it? Someone tell me. How do I solve this problem when n is 1? The tower height is just 1. Just 1 disks there. There is only a single disk. What is the answer? It's a very simple one, right? Is everybody gone? Am I still on? Yeah. So Eren is saying this is a simple one, right? So take this and put it here. Voila, the solution is there. All right. So this means that if I end up with, okay, let's look at this one. And do I care in this solution? Do I care if I have anything, let's say, anything in, let's say, in this solution, this particular solution, when I actually go from here to here, I go from here, start to end. Do I care if I have anything on the tower A? The answer is no, I don't care. I don't need tower A. And I don't need to put anything on tower A. I can actually just go straight from S to E, given what? S has only one entry, one thing, just one. And the end tower doesn't have anything on it. This is my solution when there is only one. Okay. So let's look at this case where we have perhaps, let's say, two of these only. When I have two, what do I do? So I have two. Can I solve this problem now when I have two? So when n is 1, I can solve it. I know that towers of Hanoi with 1, the height is 1, I can solve it. I know how to solve it. When there is 2, can I solve it? Still easy, right? So what do? I put this one here first. So let's do it this way. This guy, the solution to this guy is very simple. I take this guy and put it here, and I'm done. This one, I have two-step solution. I have to have 2 steps. The first step is take this one and put it here. And the second step is, so this is first step. The second step is actually put this guy here. This is the second step. And the third step, I'm sorry, we should have 3 steps. What do I do? I don't know what I'm doing here. All right, not this one. First step is I take this guy and put it on top of it here. Okay, so now this is a solution. Start from here, do this one. What did I do? Okay. So do this one, and then this, and then this, and then this. Okay. So two-step solution is also, I mean, when I have height 2 in the start case, I have a simple solution, but that solution requires the usage of A, right? The auxiliary tower needs to be used. If I don't use the auxiliary tower, I cannot actually do it. And that means that auxiliary tower should not have anything smaller, larger than the peg that I am gonna, the thing that I'm gonna put it on. So this guy is gonna be put on there. So whatever I have here underneath should be smaller than this, or sorry, larger than this. And then, and of course, when I'm here, there should be something smaller than this underneath. All right. Now, so this is kind of suggesting me a solution. Now, if you have one peg left, or one, let's say, disk left here, and if this disk is the smallest disk, I can solve this thing directly. I can just put this one on top of E here. If you have 2 of them, what I need to do is I need to actually do a kind of a swap. And for that swapping, I need my auxiliary one, the auxiliary tower. I'll put my first disk on the auxiliary tower, and then the second one on the end tower, and then move the one on top of the auxiliary tower back to the other one. So you can see that if I have left something here, one thing that is actually only one thing is left here, my smaller problem, I'm looking at a smaller problem. This smaller problem says you either, if it is possible to put it on top of E, just put it on tower E, just one entry. If not, that means that you might have something here that is actually smaller than this guy, so you cannot put it on top of there. So what you need to do is, perhaps you need to do something else. Perhaps you need to actually go and do this, and you cannot do either of them, then this cannot be actually completed. This move cannot be done. So there is a problem there. Okay. So given this, the algorithm is actually very simple. So I have the okay, let me see. So I have a function called tower. All right. And so what I am doing here is that I'm saying if n is 1, n is the number of disks to move currently from the from peg. This is the first tower. This is the to peg. This is the end tower. And this is the auxiliary peg. This is the auxiliary tower. All right. So the way that I want to do this one is I want to actually, if this is the case, so this is the first, this is the start one. Sorry, let's go back to here. This is the start one. This is start. This is end. And this is the auxiliary one. And those are just the names. I'm just keeping names here for this representation. I'm not keeping arrays here. And I'm saying, okay, this. And I'm asking how many towers you have, how many, let's say, disks you have on from peg, on start, that you need to move to peg to the end. In my original problem here, for example, for this problem, I had 5 of them, n will be 5. In this case, I have 2, n will be 2. In this case, it will be, it will be 1. All right. So this is what I am trying to do. So, okay, your original problem is you have n number of disks on the from peg, and you need to move them to peg. All right. So if n is 1, I say, okay, my answer is very, very simple. Just move the disk, this one disk, from peg 1 to, from peg to 2 peg. This is the thing that you need to do. This is very simple. We know this one. If there is only one, assuming that you can actually move this thing on, and meaning the 2 peg is either empty, nothing is on it, or there is something on it, right? There is something on it, but that thing is less smaller than, or the larger than the moving, that the one that you are moving currently. Okay. And then we say, okay, else if this is not the case, meaning you have more than one disks to move, so you do it this way. You say, okay, you take the from peg, aux peg, to peg, you have try to actually move the n-1 entries. So what we are trying to do is, I'm gonna say, okay, if you have 5 entries, okay, I know that I cannot solve this one with this one. I'm gonna say, okay, look for how do you solve for 4 entries? Of course. So it will say, okay, call the same function using 4 entries. Once you actually solve this problem, those 4 entry four things. So meaning, if you are able to somehow, let's say, if you are able to solve somehow these 4 entries here, not the 5, but the 4, meaning you move the 4th here, you move the 3 here, you move 1, 2 here, and 1 here. So these are gone here using that tower. So from S to E using A and 4 of them. N was 5. Assume that you can solve it with 4. And your algorithm handles this one. Assume it that it's actually done. Then what do I do? In this case, I have everything is actually here. This is done, but I have this guy here that is not actually done. All right. So instead, what I do is I do it this way. I say, well, in that case, if this is the case, this is what I'm going to do. I'm going to say, if that is solved, if the tower problem for that n-1 peg disks are solved, then what I do is, if this is the case, then what I do is I move my peg, I move my disk, the nth disk, this disk number 5. So this is the case that I have right now. So 5 is here. And on the end 2 peg, so be careful. Sorry, I made a mistake here. So what I did is I said, okay, so I had this 5, 4, 3, 2, and 1. I said, okay, move them to aux peg. So move them, those 4 to here. So this is 4, 3, 2, and 1. So this is what it's gonna happen with this guy here. So this is the auxiliary one. So this is A. Sorry, that's correct. That's not correct. So this is start, auxiliary, end. Instead of, so if you have one entry left, just move it from peg to 2 peg. This is this base problem. If not, assume that you can move the n-1 entry on top of 5, 4, 3, 2, 1, put them on the auxiliary peg, on this peg. So move 4, 5, 3, 2 to this one. Assume that this is possible. If this is the case, then I am done. What do I do? What I do is, I do it this way. I move this guy here, 5 here, right? The last entry. And then I actually, once I do this one, I move that 5 entry to the 2 peg. And then from aux peg, move everything to 2 peg using the from peg as my auxiliary. So now what I'm going to do is I want to actually move these to here on top of 5 using the start peg as my auxiliary. So this is very simple. So what I'm trying to do is this way. So let's look at this one again here. So there is a function that I think is working. So this is a function that I want to do. Tower. So it has start, it has end, and it has auxiliary, and it has number n. This is the function that I have. It says, give me a start tower with your n entries. Put each of these onto in tower E, right? Using, if needed, the tower A as an auxiliary. Okay, so it says if there is only one entry on S, there is one entry on S. My answer is very simple. I put it right away on top of E. If not, then this is what I do. I say, okay, hey, tower, let's call tower one more, twice, perhaps. First, move everything from S to A using auxiliary as E. So the third one is auxiliary, and do this n-1 entries. So what I'm doing is I'm saying, okay, I cannot actually move everything right now. Instead, what I'm going to do is I'm going to move these 4 entries, here, using, and I'm going to put them over here on A using E as an auxiliary. E is empty in the beginning, right? So this is possible. There is no problem with this one. So assume that this works. Assume that it worked such that now you have 4 is here, 3 is here, 2 is here, and 1 is here, and these are gone. Now what do you do? Then your answer becomes very simple. You move from where to where? From start to end, your current number n. So you move n from start to end. So now you put 5 here, okay, and now you have nothing here left, and you have your n-1 problem is currently on A, and your last entry is in E. Now, I need to get these back to here. So what do? I do this one. I say, okay, tower, take everything from A. Since 5 is in the right place, I don't need to worry about putting something on top of it. So I do it this way, using this, and S is empty, and now I have this n-1 problem left to me. So what I do is, after this, I use the same algorithm, but this time start position is A, tower A, end position is E, and my auxiliary position or auxiliary tower is A. When I do this one, this is what is going to happen in the second iteration. Let's erase them all. So 5 is here. So let's do it this way, actually. 1 here, so that don't lose track of it. Right? So let's take this guy. So the algorithm says, algorithm is very simple. It says, so you have 5, 4, 3, 2, and 1 here. Algorithm says, do you have only one entry on S? So the first time I'm calling this tower with S as the start, E as the end, A as the auxiliary, and 5 entries. Okay. It says, since this is 5, have only one entry left. So therefore, what I'm going to do is I'm going to actually split this problem. I'm going to say, okay, this can be solved into 3 steps. The first step is move the tower from S to A, move everything from A, use as an auxiliary one, and using 4 of those disks. So for the first 4 disks, move them to A, and assume that this is working. And I'm going to show that this is working, but assume for the time this is working. So if this works, then this is what you are going to end up with, right? So this is going to be 4, 3, 2, and 1. And there will be nothing left here. These guys are going to gone. Okay. Now this is after this tower SAE4, this is gonna what I'm gonna have. Now this is a simple problem. Then I can solve this by move. Just saying that. Just move now. What do I move? Move 5 from. So move 5 from S to E. This is the second step. This is the basic step. So what I am going to do is 5 is going to end up here, and 5 is going to be raised here. All right. And then the next stage is going to be a third step. It's going to say move, call tower. This time move all those 4 entries on A from A to, using this guy as an auxiliary now, S, those 4 of those entries. Assuming that this works, then we are done. We don't know if it is working, or you don't trust me if it is working right now, let's say, okay? So, but I know that if right now, this specific solution, if tower, this tower and this tower, then I'm able to actually put all these things here, 4, 3, 2, and 1 this way. So the question is, would actually it work for smaller number of entries? So for 5 entries, it is working, assuming that tower works for smaller number of entries. Let's look at it. Look at the case. So if I had 4, 3, 2, 1, what would happen? It will be the same thing, right? It will say move tower from S to A using E as an auxiliary. E had something, I don't care what E has actually. It doesn't matter. Using 3 entries. So then this will be 3, 2, and 1. And then the last entry from here to end, this is the second step. The third step said, if you recall, move from A to E using this S as an empty or a intermediary or auxiliary peg, move those 3, okay? If this works, if both of them works, I'm done as well. So now let's look at actually if it works for 3 cases, right? Or three of these. So 3, 2, 1. Same thing, tower, start from S, go to E, using A, move 3 things. Is in this case is gonna be meaning that I'm gonna take actually S to A, using A as an empty thing, and move 2 things. This is the first step of my algorithm. So this will say 2 and 1 here, and then it will move 3 here, and then it will move 1 and 2 here, assuming then 1 and 2 can be moved anyway. All right. So let's go look at 1 and 2 cases. 2 and 1. 2 and 1 says, okay, take the 1, put it here, and take 2, put it here, and take 1, put it on top of here. Now, I don't care what is actually underneath, because I'm guaranteed that I'm not going to actually put anything underneath, as long as, and my first step, if you recall, this step, the first step was putting everything here, 4, 3, 2, 1, and then 5 here. So when I actually do this again, there will be always 5, which is larger than this guy, right? And when I do this for 3, it's going to be the same, and 2 is going to be the same. So it seems, as you can see, this algorithm actually works fine. So the way that it actually works is very, very simple. So let's go back to the algorithm. It says, if you are moving something n of those disks from peg to 2 peg using auxiliary pegs, if you have only one of them, you are done. You move it from the peg to 2 peg and done. Otherwise, you do 3-step process. The first step is you move everything but the last entry from peg to auxiliary peg using 2 peg as your intermediary auxiliary peg. And then you move your last disk from the peg to the 2 peg, and then move everything from your auxiliary peg, which is 4 of them right now, to 2 peg using peg as your auxiliary peg. And as we can see that this will actually give you smaller and smaller and smaller problems. And then at the end, when you reach the smallest problem, that's your base case, which you move just right away. And the rest is actually going to work out very well. So here, I'm going to actually just printing the actions that I'm going to take. The action is I'm moving disk 1 from peg to 2 peg. And then this will actually move the disk n from peg to 2 peg. And when you run this guy using, let's say, with a 3 case, so when you have 1, 2, 3 in the A, C, and B, this is what you have, let's say. If this is the case, so what you've, since what you are going to do is you are going to call tower B. So you're going to say, okay, put D into, first of all, B. This is the auxiliary one. The first step, this is this guy. And then you move your to C here. So this is 1 and 2. And then you move back your 1 and 2. This is this guy, back to C, 1 and 2. All right. Assuming that this is done. And let's see if it does it this way. Yes, when you look at this one, it says you move your, when you are here, you move your one disk from B to A using the C as an auxiliary, and then move the 2 from A to B, and move B to A using the auxiliary C, the 1 path. And this will actually do the movement from start pack to the end pack, or start pack. But this will be the answer. Move disk 1 from A to C, move disk 2 from A to B. So you have, let's say again, assume that this is A, this is C, and this is B. We want to move everything from A to C, right? So 1 to, you move disk from 1 to A. So you move disk from 1 to A. 1 to C here, and you move disk 2 from A to B. This, right? So this is gone. This is gone. And then you move disk 1 from C to. So I should have wanted to do it this way. 1 and 2. All right. So now you want to be the one that you have. This is the one. This is gone. And then 3 to A to C. It's gone from here to here. This is 3. Right. So let's erase them. So now C is 3. And then move 1 from B to A. B to A, 1 goes this way. And 2 from B to C, 2 goes from B to C here. And then 1 from A to C, this goes here. So that 1 to 2 power 2 to 3. Now you can see that this code is extensive. Actually, you have 4 lines of actions, 4 different actions, and 1 check. For one case, you have 1 action, and then for the recursive case, you have 3 actions, and you are done this entire problem. If you want to do this with the different algorithm, it will be very like a loop or something like this. Possible, and you cannot use it. You cannot do it without a particular data structure that you don't know yet. So you need a kind of a stack here to actually solve this problem. You cannot solve it just using simple iterations or simple loops and function calls. So I hope the sound was not so bad in the second half. I hope. See if I'm going to do this session next week, or we do a makeup session. For this. All right. So with this, I'm gonna stop the recording, and I wish you all next Tuesday.